it's possible you'll be asked to describe or to sketch the relationship between pressure, volume, and temperature for an ideal gas. So if you remember the ideal gas equation, you're given this in the exam, of course, PV equals nRT. Now, the three things we're interested in, P, V, and T. So P, V, and T. So there are three relationships you need to watch out for. So one is PV equals constant. That means pressure is directly or inversely proportional to volume. So that's the same as saying P1 V1 equals P2 V2. So that's your first relationship. Second relationship you need to watch out for is volume and temperature. So here we say V over T is constant because they're directly proportional. Okay, so V1 over T1 equals V2 over T2. So these are two really important relationships, and the third one is P and T. So pressure and temperature are directly proportional, so P1 over T1 equals constant. So, or P over T is constant. So P1 over T1 equals P2 over T2. Now, you need to understand that there is a condition along with each of these. So for example, here, PV is constant only if T is constant at constant temperature. We call this isothermal. So if there's no change in temperature, we can use this. If there's no change in pressure, we can use this. We can say at constant pressure. Okay, so, and here, this is true at constant volume. So we can only use this expression if the volume is constant. Now, you may be asked to sketch these relationships, okay? And it's fairly easy. When things are inversely proportional, like pressure and volume, the graph looks something like this. So if you had P here and V here, then as the pressure increases, the volume decreases. So you could sketch the graph like this. Okay. And if you had the same kind of graph required between volume and temperature, then it would look like this. This time they're directly proportional rather than inversely proportional. So V over T, the relationship would look something like this. And you'd have, it doesn't matter which you put on which axis, but generally the dependent variable would be on the y-axis, so Vt. And finally, if they ask for pressure against against temperature, then you'd also have a straight line like that. Okay, so whenever you have direct proportionality, you have a straight line. Whenever you have inverse proportionality, you have something like that. Now they could ask, what would happen if the temperature was increased? And the answer is you would have a family of curves. So you'd have curves that might look something like this as the temperature increases. Okay, maybe I should make it a little bit more curved. So as the temperature increases, this would happen. And here it's at constant pressure, but if the pressure were to increase, then the volume would decrease, and you'd have lower lines like that for lower pressure. Okay, if they only ask you for one graph, then just give them one with a lower slope. Here, volume is constant, and you have pressure against time. But if volume was to increase, then the pressure would decrease, and you'd have a line like that. So this would represent increased volume. And if the volume were to decrease, you would have a line like that. So let's focus on increasing. So if volume increased, that's what would happen. And if pressure were to increase, you would have that. And if temperature were to increase, you would have that. So it's fairly important to be able to draw these. Okay, so be prepared to either describe these relationships or look at a graph and decide which expression you can use, or be prepared to comment on the differences between two graphs. So here you have a higher temperature. Here it looks like we have a higher pressure. Here it looks like we have a greater volume. Okay, so I hope you found that helpful. This is in relation to pressure, volume, and temperature graphs for ideal gases.